Hello everybody, welcome to my talk. This is Pierre Talbot speaking to you, and this work is in cooperation with Eric Monfroy and Charlotte Truchet. We'll see a technique to combine constraint solver. First of all, as we know, there are a lot of research communities that are centered around some solving techniques in order to treat different constraint languages, such as SAT solving for propositional formulas. Then you have linear programming, constraint programming, answer set programming, and you have many others. And it's even larger if you consider heuristic approaches, such as genetic algorithm, evolutionary algorithms, or local search. So the challenge is that each of these fields, they have their own theory and terminology. This is a good thing because it allows a community of researchers to speak the same language and to develop really efficient algorithm. But on the other hand, when you want to change your field or to get inspired by another field, it becomes really hard because you need some time to understand the new theory. And that's a bit unfortunate since it's to solve the same kind of problem. So the overarching project of this paper and the previous one, and hopefully the next ones, are to take a step back and to try to find a unified theory that would encompass all these fields. The candidate theory we propose is to use abstract interpretation, which is initially a framework to statically analyze programs, and it has some interesting features for constraint reasoning. First of all, it has a solid mathematical background based on lattice theory, and it has this concept of abstract domains, which are lattices with some operators and that are able to encapsulate a constraint language, or if we take some liberty, constraint solver. So you can equate for now abstract domains to constraint solver. The good thing with abstract interpretation is that it comes with a different product. So you can combine these abstract domains, and then you have a notion of under and over approximation, which maps into soundness and completeness result of constraint reasoning. Little bit of context. So all of what I will talk about today is implemented in a solver called Absolute, started in 2013, mostly initially over continuous domains, and last year we investigate under approximation and discrete constraint solving within the same framework. In this work, we focus on domain transformers, which are some kind of abstract domain that takes as parameters other sub-abstract domain, and then they can interact with these subdomains to make them communicate information. We'll see two domain transformers to combine abstract domains that are sharing variables. The first one will be interval propagators completion, and the second one the delayed product. Then we'll see a third abstract domain, which will be useful to combine domain transformers. I will introduce first abstract interpretation for constraint reasoning. Then we'll see the domain transformers I just mentioned. So just a simple diagrams of abstract interpretation for constraint reasoning. We start with a logical formula, and then we can interpret it concretely, which means that we take all the possible mathematical solutions of this formula, which are not necessarily computable. So since it's not computable, we need a counterpart, which is called the abstract domain, which will be computable. And we have the equivalent here, the abstract interpretation function. And then we can go from the abstract to the concrete domain with something, the gamma here, which is called the concretization function. Let's take an example, which will make things simpler. So here, a really simple logical formula, which is just the bounds of variable x. The concrete domain in this case will be the power set of the real numbers, and the abstract domain will be an interval floating point number. Of course, the concrete domain, we cannot have a set of an infinite set in the computer. We need to have an abstraction of that. Now the for this formula, the element of the concrete domain will be this set, which is infinite. And for the abstract, we can imagine having this set. So this set, not this set, this interval. So this interval, it has a little problem, let's say, it's that it contains the value 2.25 and 2.75, which are not solution. When the abstract element contains elements that are not solution but contain all the solution nonetheless, we will talk about an over-approximation. The opposite is an under-approximation if the abstract element contains only solution but not all. And now let's just see quickly what is an abstract domain for constraint reasoning. We'll talk about lattices here. So it's just some set and with a partial order. So here we'll see that if B is greater than A, then we understand it as B contains more information than A, or that B is more solved than A. Bottom is the smallest element, that it's if you know nothing when you start a computation, basically. The interpretation, concretization function we saw. Closure operator. So this one is, for example, if you are a SAT abstract domain, then that would be the unit propagation or the propagation in constraint programming, etc. The split operator, which just divide an element into several parts, and the state, which tells you if an element is a solution or not, or we don't know yet. A solver using any kind of abstract domain, so it's generic. It really looks similar to the one you would find in a constraint solver. So you just apply the closure operator, which is the propagation. If you reach a solution, you return it. Otherwise, you return the empty set. And if you don't know yet if the element is a solution or not, then you can split it and you recursively call solve on each of the sub-problems. Initially, you can call this algorithm with the abstract interpretation of the formula, and this one will map to the solutions of the formula phi. Okay, that's it for the quick introduction to abstract interpretation for constraint reasoning. Let's now see the main contribution of this paper, which are domain transformers. The most simple domain transformer is called the direct product. So imagine you have a formula where you have the constraint in blue that has interval constraints and that can be treated in an interval abstract domain that we call box. And you have the green constraint, which can be treated in the octagon abstract domain. Now, this constraint doesn't share any variables in common, so you can just call these abstract domains independently from each other. And this is exactly what the direct product is doing. So, for instance, you can define it, all the operators of the direct product are defined component-wise. So, for instance, here the closure operator will just call the sub-closure operators of all the sub-abstract domains independently from each other, which means that these subdomains will not exchange any information. Now, consider this formula with three constraints. First one can be treated in box. The third one in green can be treated in octagon, as we saw before. But this time we have the red constraints, which actually share some variables between the box and the octagon's abstract domain. Actually, this constraint can be a bridge between these two abstract domains. So this constraint can be treated in a linear programming abstract domain called polyhedron. But that doesn't solve the problem that with the direct product, this constraint will not exchange any information. So we need something more that will synchronize the variables in each of these abstract elements. And for that, we have this notion of propagator functions, which are extensive function over lattice, which can be used to connect variables between abstract domains. So let's see an example of our propagator work in the context of abstract domain. First of all, we need to equip the abstract domain with a projection function. This function takes an abstract element of variables and projects the lower and the upper bound of the variables in the domain. let's do it with two variables, x and y, then we obtain these two intervals. And now we can interpret this constraint into a propagator function, which takes an abstract element as a parameter, and which join into this abstract element new bound that can be inferred with this constraint and the current domain. For example, we know that x must be greater or equal than the lower bound of y, otherwise this constraint cannot be satisfied. So this is an example of propagator. Now we can actually design a domain transformer of propagator, which will just take a base abstract domain and a set of propagator functions. Of course, this abstract domain can be the direct product of two domains. So for example, here that's what we do, and we do the direct product between box and octagon. And then we can add into this domain a propagator for this constraint, defined in a similar way to this one. Once that is done, each time we'll call this function and we'll perform the join operation, then the new bounds infer on each of the variables will be automatically transferred to the right sub-abstract domain because thanks to the direct product. IPC exchanges bound constraints. So can we do better than exchanging just the bounds? Yes, we can, using the delayed product, which is inspired by the delayed goal of logic programming, where a goal is delayed until a variable is instantiated, using the freeze predicate, for example. So here we do exactly the same. We have the same formula, and the constraint, the red constraint, will just treat it in IPC, so here, as before. But whenever x becomes instantiated, let's say to 3, then we'll transfer this constraint into the octagon because it can be treated there more efficiently. We can do a little bit better than that, and we are not necessarily required to wait that this variable x is instantiated. We can instead take the lower bound of x and send over approximation of this constraint into the octagon. For instance, if x is between 1 and 3, we can already transfer this constraint because we know that we will not lose solution by propagating this constraint. All the solutions of this constraint are necessarily included into the solution set of this constraint, which is formally stated as follows. Finally, really quickly about the shared product. Now we have two different domain transformers. Then how do we combine them? The problem is, of course, if these domain transformers, they share subdomains. So our solution is just to use something we call the shared product, which is a top-level product that combines abstract domain. And in the closure operator of this domain, we'll merge the shared subdomain using the join operator of the abstract domains. So more detail about it are in the paper. About the application, we chose the flexible job shop scheduling, just because it has some temporal constraints with 3 variables. So whenever the duration here of a task is instantiated, we can send it into the octagon. So that was a nice problem to try the delayed product. And the results are rather competitive. It depends, of course, of the instances. But our goal was not really to beat the benchmarks, but mostly to prove that it's feasible. And with a combination of basic technique, we can still obtain really, really good efficiency. To conclude, you might wonder about the difference between our work and SMT solvers. Well, I think it's not a big difference. It's just that SMT solver are studying combination on the logical level, while with abstract interpretation we are studying it more in the semantic level. A difference, though, is that in SMT solver, usually the cooperation scheme is fixed. You cannot easily change it unless you are rewriting the combination of the theory in your solver, and you can certainly not run several cooperation schemes concurrently in a modular way. So I think that's what our system achieves that SMT doesn't currently achieve. Another work, more theoretical, is abstract conflict-driven learning, which is also abstract interpretation and constraint reasoning, but with conflict learning, something we do not have yet in our solver. It's really nice, but it has not been experimented a lot on constraint reasoning problems. And finally, you have this nice constraint logic programming language named Toy, which has this notion of bridges among variables. And I think, at least for the bridges concept, it's subsumed by our abstract transformer IPC. Finally, to conclude, we have a kind of mapping between constraint solver and abstract domain, and cooperation schemes and domain transformers. We have described two cooperation schemes, IPC and the delayed product, and then how to combine these cooperation schemes. I think that's the novelty of this work, is that you can have several cooperation schemes inside the same system and that they can be interchanged in a modular way. So all the experiments are available on GitHub at this link. Thank you very much for your attention.